Hello everybody, it's Pablo Fertyk from Miskatonic Studio. Some time ago I created this Aurora Borealis effect using a raymarching shader in Godot Engine, and the source code for this shader is already uploaded to godotshaders.com and to GitHub. But some people were asking me to create a tutorial for this shader, and I finally found enough time to record this. I think despite the source code being already available, it would be nice to explain what's going on so that you know how to get from an empty project in Godot to this effect, and so that you can easily adjust it to your own needs and create your own awesome effects. So let's go. So let's start with an empty scene, a 3D scene. Let's call it tutorial. And let's save it in the tutorial folder, why not? Now you can see that this is not the default sky that Godot Engine provides. This I've changed it to use a custom color and turned it to black. That's because we are creating a very shiny effect and it's not that nicely visible and with a bright sky in the background. So I'm remove the color from the background so we can focus on the shader effect itself. In this empty scene, let's create a mesh instance. Let's rename it to box. We can use the cube mesh to make things easier. And let's create a shader material, and that shader material is going to have a shader that we are going to immediately save. So tutorial GD shader, also in the tutorial directory, and let's edit it. So this is going to be a spatial shader type, and to make it visible we can change the mode to unshaded for now, unshaded, and let's create an empty fragment function. And in that fragment function, let's set the albedo color to vec3 1.1, so white. So yeah, this does not do anything yet, but it's the basis for our future raymarching shader. Now, before I move on to an actual raymarching shader, I will have to explain some theory, so bear with me for a moment. So this is how a fragment shader looks like without raymarching. Fragment shader, as you may know, is called once per pixel, and when it is called, it receives a lot of input values. It receives the normal vector at this point, that's the vector of the perpendicular to the surface of the mesh that this pixel belongs to. It receives information about the light, it receives the UV coordinates and some other things. And using all that input information, fragment shader calculates a new material and returns it. So basically, we can create many different magical effects using math in the fragment shader, but we return material once, right? And we return it based on the information available at this point where the pixel is. Now, with raymarching, it is a bit more complicated. Raymarching, instead of stopping at the surface, it's still a normal fragment shader, so it is called for a single pixel with all that input information, but the raymarching shader enters the mesh itself in a series of small steps. So it calculates the next step in this direction that we are looking, that is now located inside of the mesh, and then and in that step it can gather additional information and then moves on to the next step and gathers more information, and so on and so on and so on, until we run out of steps, or we run out of this distance, or we run out of the mesh itself. It depends on how we write the shader. And when it's done with this loop of steps, the fragment shader aggregates the results and returns again a material at this point, but this time this material can take into account what is happening inside of the mesh, which allows us to create many awesome effects. For example, you can create a function that determines if a point is inside of a cloud or outside of a cloud, and depending on that, you can add more density if a point is inside of a cloud, and when you get the final results, it will look like this mesh contains different areas with different densities, so it will look like a very realistic cloud. More precisely, a raymarching shader needs some additional information that are the origin of the ray that we are tracing. So this is basically going to be the location of the camera. Then we need the direction of the ray, so the direction where we are looking at, preferably normalized, but yeah, we can do it in the shader itself. Then we need the distance between the origin and the surface of the object. So this is basically our starting point. There is no point in doing ray tracing calculations before this, only after this, right? So this distance is a starting point for us. And then we need the length of the step, so that we can calculate those smaller points that are located inside of the mesh. And also we need some kind of condition to end ray tracing, because without it we are going to end up with an infinite loop, and this is going to crash our machine probably. So we either set a specific number of steps, or we set a specific distance that we are going to trace this ray inside of the object, or this is something that we are going to implement today. We are going to check if these points are still inside of the mesh, and as soon as we leave the mesh here, we will stop ray tracing. Ray marching, sorry. So yeah, with all this additional information, we can actually start writing our own ray marching shader. So knowing what we know, we can now proceed with writing our own ray marching function. And I will make that function return a float, and I'll call it ray march. Now, why a float and not a color? Because I would like to start with something simple. So, and yeah, it needs to return something. So return 1.0, let's say. This function will basically return the density inside of this mesh, inside of this cube. The higher, and then later in the fragment shader, we are going to turn the density into an emission color and also into transparency. So where the density will be like low, then the transparency will be bigger. So we will end up with these streaks of light. And yeah, I think the effect is quite nice. But just to simplify things, instead of returning the color itself, we are going to return the density in a given pixel, for a given pixel. So yeah, actually let's call this float density equals, let's say 0, 0 maybe, and return density. Now, we already mentioned that we need some additional information like origin, distance, step, and direction, right? So let's put them as parameters here. Vec free or maybe ray origin. Also vec free ray direction and float start. Now step, instead of putting it as a parameter, I would create a constant out of it. Const float step equals, let's say 0, 0, 0, 1. I want really small steps. The smaller steps that you are going to use, the more refined the effect is going to be. But yeah, but also there is going to be a lot more calculation involved, so you need to balance this. Right, so we know that our function is going to return the density for a given pixel, and it already has these three input parameters, and it knows the step. So let's start with float distance. I would call it distance, but it's a a keyword in Godot, so let's call it dist equals start because this is where we start our calculation. So the initial distance is going to be equal to this. And then we are going to run a loop while true. And true loops are very dangerous, as you might know, because if you don't put a proper condition to end this loop, then we are going to end up with an infinite loop. So let's put that condition immediately. Let's calculate. So with each iteration of this loop, we have to calculate the point inside of the mesh, and the point is going to be vector free point, and it's equal to ray origin plus ray direction times distance. And what we are going to do now is we will add that condition to check if the point is still inside of the mesh. And the mesh, for simplicity, is a cube. So this cube ranges from -1 to 1 in all directions, right? In all three directions. So to check if the point is inside of the cube, I'm going to do this. If clamp point vector free -1 vector free 1 is not equal to point, then we are going to break. So I think I'm missing, yep, I am missing a bracket here. So what is happening here is clamp method takes a value and takes two thresholds. If the value is between those thresholds, then it is returned as is. If it's below one of the threshold, the lower threshold, then we return the lower threshold, and if it's above, then we return the upper threshold. So basically, and it works with floating point numbers, but also with vectors. So if this vector is below -1 on any axis, it will be modified, and also if it's above +1 on an axis, it will be modified. So if it's not modified, it means that we are still inside of the whole box, and if it has been modified, it means that we have reached the outside of the box, and in that case we need to stop raymarching. So yeah, and well, we have the point, but also the point is calculated with each iteration, but we also need to calculate the distance. So go to dist plus equals step. Yeah, so with the next iteration, this distance is going to be a bit longer. All right, so this is basically the loop itself, but it doesn't do any calculations regarding the density. It's just it makes a point. It checks if that point is outside of the box, in which case we stop the loop, and then it increases the distance. So now the calculation about the density itself is going to have to be put here. And let's start with something very simple just to illustrate the point. So let's say density plus equals 0, 1, which basically means that every time with each of those points, the density will be bigger. And if we reach the outside of the box, we will stop increasing the density, which means that the bigger the distance we can travel through the box, the bigger the density will be. So let's try to use this function now. The only problem being that fragment shader does not have information about the origin of the camera position and the direction where we are looking. So in order to put that information in the code, we will have to use a vertex function, but and in order to exchange information between vertex function and fragment, we will have to use varying variables. So let's create varying vec free camera and varying vec3 position. Okay, and the position will be not the position of the camera, it will be the position of the pixel in the 3D world. So knowing that, let's move on to the void vertex function. And here we are going to assign values to those two vectors. So camera equals. Now this is a formula to calculate the position of the camera. You just have to copy it basically. Model due matrix times vec4 0 0 0 1 xyz, and position is vertex. So vertex function has access to that variable, fragment function does not. So now we are going to use that in the fragment function. So vec3 ray origin equals camera, and vec3 ray direction equals normalize position minus ray origin. All right, and now we can calculate density by using our raymarch function. So yeah, float density equals raymarch ray origin ray direction, and the distance, the starting point, is the length of the camera vector minus position vector. So the position being the point, the vertex coordinates, the pixel coordinates, and the camera being the place from where we look. These two, the difference between them is the point where we start. So now we have this density. So let's, instead of let's keep this as 1.0, but let's modify the alpha value to density. Yeah, this is not exactly what we were looking for, and that's because this condition here checks if that point is inside of the mesh or outside of the mesh. The thing is, when we start with an actual distance between the camera and the point, we will start with the surface of the mesh, which can be inside or can be outside. So that's not exactly the effect we are hoping for. The simple solution is to just add step here so that we start already one step into the mesh. And it might not look like that right now, but you can see here on the edges, this actually is a semi-transparent object. So that's because the density is probably a bit too large. All right, let's modify. So now you can see that there is a fog going, the mesh looks like it's filled with fog, which is exactly the effect that we wanted to achieve. So the only problem I could see right now is that density is fixed, but theoretically we could modify the step value, in which case this calculation, this whole loop would happen more often or not as often as now. So we would end up with different, so let me just illustrate. Yeah, we will end up with different values of this fog. So to avoid a problem with the value of the step affecting our final results in any other way than the results being more or less refined, let's create a uniform form float base density equals, let's start with 1 0, and here the density is going to be base density times step. And now it's a bit too big, but we can turn it to like 0.1. Nice, yeah, okay. So now if I decrease or increase number of steps, the final result will not differ that much, which is exactly what we wanted to achieve. Now the next step here is to change the density of this fog, because right now it's uniform in every direction, and what we want to have is we want a really dense effect at the bottom of this mesh, and then we want it to slowly dissipate to go to 0 at the top of this mesh. So in order to do that, we can use this point that we calculated, and this point has coordinates inside of this object, so they will be ranging from -1 to 1 in all directions, and we can just use the y coordinate of that point. So let's do that. Let's introduce a new variable from height factor, and let's put it as point.y, except point.y is going to be from -1 to 1 on the y-axis. But what we want is, we want it to have from 1 at the bottom to 0 at the top. So we are just going to modify this a bit. Basically this value is from -1 to 1. So let's add 1.0. Let's subtract it from 1.0. This will like flip the value, and then let's multiply it by 0.5. So like this being from -1 to 1, this will put it to from 0 to 2, and this will scale it from 0 to 1, but 0 being on top and 1 being on bottom. All right, so we have this height factor, and let's I think I lost base density here. Oh no, sorry. So we actually have to move this here and multiply the step times height factor, and you can see that the mesh now kind of starts really thick here, and then slowly the fog becomes weaker at the top of the mesh. Of course, we can still modify the base density. We can maybe make it like 0.01 to see the effect even better. These values we can later play with to achieve a specific effect. But for now, we are still using a fog that is more or less the same in every direction, except now it's the same in all the XZ directions, right? We modify it on a y-axis, but XZ stays the same, which is not exactly what you want. So the next step is to use a texture here. So I have already prepared a very simple texture just to illustrate another step in this tutorial. The texture looks like this, and what we want to have for in the next step is to have this fog recreate this pattern. So to do that, we need to add another uniform, which is going to be a texture sampler 2D, and I would call it noise, because we are going to start with a pattern, but then we are going to move to open noise textures. So let's start with noise. Let's call this a noise, and then let's go to the box to shader params here, and we can just drag this texture here. And now inside of the shader itself, so what we need is we need to calculate the UV coordinates on that pattern texture. We can use the X and Z coordinates of the point that we calculate here, but again we will have this small problem that the coordinates of the point go from -1 to 1, and the coordinates of the texture go from 0 to 1. So we are going to calculate our UV coordinates on our own. vec2 uv equals vec2 point xz plus vec2 1. So this is we take the x coordinates ranging from -1 to 1. We move them by 1, so now they are ranging from 0 to 2, and now we are multiplying it by half. So this will make these coordinates work with be in between 0 and 1, so we can use them as UV coordinates for our texture. Okay, so now having this, okay, I can remove these empty lines actually here. So we can create, let's say, float noise value equals texture noise UV, like so. So this is actually red green. This is so this returns a color, and we because the texture is black and white or a grayscale, we do not need like all the values will be the same, red, green, blue. So we can take any of those values. Let's say red, and now we have this base density equation. So the equation's density is base density times step times height factor times noise value. And if you now take a closer look, you can see that the texture, the fog actually recreates this pattern. And if you use this gizmo here to look directly from the bottom, you can see that this is, well, it's rotated a bit because of how the coordinates on texture work versus the coordinates in 3D space. But you can see that this is the exact same texture, right? So this is a very important step. So now our fog can be put into a specific pattern. The only problem is that this pattern comes from a static texture for now, and what we actually want is we want to have it moving. We want a dynamic pattern, and we will achieve that using a noise texture in Blender, in Godot. All right, so now let's switch from this texture to a noise texture. Godot has an option to generate noise on its own, so we can switch to we can change the type of texture here, and then we also need to select a new open noise value. I would go with seamless, and I would probably change this to 256. That will be useful later. So if we now align the view from like top down, we can see that this is a completely different texture that we used before, which is good, but it's not moving yet. So let's make it move. Godot offers this value called time. So we have this. So here, where we read the UV coordinates of a texture, we can just add a vector 2 made out of time. And you can see, so now basically this UV coordinates will be moving as the shader is processing. But this is definitely too fast. So let's create a new uniform float speed. Let's call it speed, and maybe 0.1 would be a good value for now. So now it's time times speed. Right, so now it's moving, and it's moving slower, but it's still basically a static texture that is moving. This is not exactly what we want to achieve. In order to achieve that effect of like this waves appearing in different places on the texture, we will have to do a bit of extra calculation. We are going to basically take this noise texture, read it twice, but at different places, and we are going to combine the results of that of those two different places using a smooth step function. So smooth step function in Godot, I mean smooth step function in general, takes two thresholds, lower and upper, and if the value and it takes a value, and if the value is below the lower threshold, we return 0. If it's above the upper threshold, we return 1, and in between it is nicely interpolated, as you can see on this graph. So we are going to use that to combine the results of those two texture reads. Plus, we're going to apply some distortion and other operations. So this is basically where the magic happens, how to take a noise texture and turn it into these seemingly random waves. Okay, so because this shader involves a lot of tinkering with different values, I would start with creating a couple of more uniforms here so that you can later use them to fine-tune this shader. So we already have speed of the shader. The standard is also to create an offset. Let's say it would be like 0.08. It's just a value that I came up with when I was fine-tuning my shader uniform, but maybe you can find better ones. So we can also add a value for scale. This is the scale of the noise texture. Let's start with 1.0. And yeah, because we are going to use the smooth step function, let's add float smoothness, and let's start with 0.15. Yeah, so having these additional values, we can move on to this. So we already have the UV coordinates on this plane, the XZ plane. This time speed is going to be used in more than one place, so let's extract it to a variable. Float time equals time speed times speed. Now let's calculate the UV1 and UV2 coordinates. So vec to UV1 equals UV times scale. So this will allow us to scale the coordinates nicely. Plus vec 2 time plus offset. And then vec to UV2 equals UV times scale plus vec 2 time, let's say minus offset to spice things up. All right, and now the thing is, if we are going to use time on both of these places, then once in a while I believe these textures will synchronize and we will have like a blast of lightning, because the whole screen will be, the whole texture will be white, so there is going to be a lot of emission in the final effect. So let's just move them slightly apart by adding this. And now, instead of reading the noise value from the texture itself, we are going to read it, to calculate it from these both texture reads using the smooth step function. So smooth step, and the first value is minus smoothness. The lower threshold is minus smoothness, the upper threshold is smoothness, and the value is going to be texture noise UV1 dot R. You can use any other color. I was going to use the red one because the textures are grayscale, so it doesn't matter. Minus texture noise UV2 dot R. And yes, so now we have a bit of a more interesting effect. It's still not the exact thing that we wanted to have, but we are slowly getting there. So what we're going to do now is we're going to spice this up with a bit of distortion. So we are going to this will really change the effects, as you will see in a moment. So we have this UV calculated here. Let's calculate vec to UV distort. Sorry, and let's make it. Let's make this value also random. So it's going to be texture noise red at UV coordinates times RR, and because again we can scale this, so maybe let's create another uniform, distort, and maybe let's start with 0.5, and we can add this multiplier here, distort, maybe distortion actually. So now we have this UV distort, and we are going to add it to both of these UV coordinates. And that gives us a slightly different effect. Still not exactly what we wanted, but now you can see that this is nice. This pattern is changing in a more interesting way, right? So you can see that this looks actually like more of a cloud at this point, but what we actually want is waves instead of a cloud. So this is going to be our next step, and we are going to achieve that edge detection by performing some additional operations on the smooth step result. So basically you can see that there are white areas here, black areas here. We will try to calculate the edge between them and use that in our shader. So this is what I've shown you before, how the smooth step function works, how the result looks like. So we are going to, it goes from like 0 to 1, and in between the thresholds it's interpolated. What we are going to do is, first we are going to move this whole the values down by half a unit, so that half of it is below 0. Then we are going to apply use the absolute value of that function to create this spike here. But the spike is pointing downwards. What we want is to point upwards, so we are going to flip it by subtracting it from 0.5, which is much. Now we kind of have this edge here, between the areas that were white and black, but it's between 0 and half. So what we need is between 0 and 1. So we are going to multiply it by 2, and that's how we are going to change this smooth step function into this edge. So back in Godot, we are going to revisit our shader code, and we are going to apply those exact operations. So here we have a smooth step value already calculated. We are going to do step by step those calculations that I just mentioned. So noise value is going to be equal to noise value minus 0.5. That's the first step, but then we take absolute value from that, APS from that, and that's from 0 to half, but in a wrong way. So we can already see that we kind of have waves here, but they are black instead of white. So now we are going to take 0.5 minus this. So now the edge is we reversed. It's reversed, right? So we have white value where the edge is, and black value everywhere else, and then we're just going to need to multiply it by 2. So now we have we turned those dynamic clouds into dynamic edges, which is very nice. The transition is still a bit smooth, so what we can do here is we can just use the power function to enhance these edges. So the closer something is to 1, the more it will stay there, but things that are like below will be reduced, will move closer to 0. So noise value equals equals power noise value, and let's say 16 should do, and there we go. So this is also something that you can put in the uniforms later if you want, but you can see now that I can see that our density is a bit too low at this point. So let's use something better. Yeah, all right. Yes. So this is the effect of the random waves appearing out of nowhere and moving in random patterns across the screen. So this is all achieved using noise texture in Godot. So nothing that we had to prepare that Godot didn't have already inside. So this is a lot of progress since we started. We just need a couple more steps to turn this into an actual shader, as you saw at the beginning. Okay, so let's proceed with the final steps. As you can see, we are still operating with the albedo value here, and the proper shader should use emission instead. So we can, well, first of all, I would like to have to be able to change the color of that emission. So let's create add two more uniforms. Uniform vec for color and let's give it a hint color, and uniform float emission strength equals, let's start with 5.0, and yeah, we can go to the shader params, and we can set this to something green, like so. We can later also change this. And yeah, so now back in the shader. First of all, if we're going to use emission, we have to remove this unshaded part. Now the whole thing is like, because we don't have any light source, so emission equals density times color RGB times emission strength. And because the original density is rather low here, let's set it to maybe 1.0, and we can see the results are now visible. We can probably make it even bigger, but in a moment. So we have the emission set, we have the albedo should also be actually set to color, I guess. So yeah, so let's set it to color RGB times density. Small typo. All right, so yeah, this is our box with a shading. So you can see that we started with a square box, okay, but I guess we don't need that much that much space in the y direction. We should more make it flat, I guess, a bit flatter at least. So let's go to transform and set this to 0.5. So now, yeah, now we have these waves looking more like an actual Aurora Borealis thing. And yeah, I guess we can also change the speed to something slightly lower, maybe 0.01, to have this nice and slow effect. And yeah, this is basically a finished product. All right, yeah, so this is the shader that we've been working on so hard. So you can use all of these parameters to modify it. You can, for example, increase the density and create this effect much stronger. Yeah, feel free to like experiment with this and maybe reuse this tutorial to create other interesting effects, either with this shader or with other shaders that you would like to work on. I'm very happy that you stayed with me for the whole thing. And as I mentioned, the source code of this tutorial is uploaded to of this shader is uploaded to Godot Shaders and also to GitHub. But I will link the both in the description. But also I would like to mention two other shaders that that were really inspiring by working on this one. First is the electricity shield shader, that basically describes how to turn a noise texture into this amazing edge detection thing with this that is so useful for Aurora Borealis effect. This I will also send a link for this one, and the other one is available on Godot Shaders. It's raymarching in a box, which is a rather short one without any distractions. It shows you how ray marching actually works and what you can achieve with it. The effect is quite nice, and yeah, if you want to see how another example of ray marching in Godot, then this would be it. So yeah, thank you very much for watching, and I hope this tutorial helps you to create your own amazing stuff. And if you do, please let me know. I would love to take a look at that as well. And yeah, thank you again, and have a great day. Bye.